Welcome everyone to this lecture. We are going to do a question in this one. The question belongs to the book H.C. Verma. It's the second last question of the chapter Electric Fields and uh, Tension. So let's begin. We basically have a charge configuration like this, some positive charge and some negative charge. Now in this configuration, there is an electric field present along the axis of the dipole. Now what is the axis of the dipole? Dipole's axis is from the negative charge to the positive charge. So it is in this direction. So roughly in that direction, I kept the electric field. So initially the dipole was kept like this. It was having this direction just like that of the electric field. Question says that we are given that this distance between the charges of the dipole is fixed by a rod. So that rod is basically a light rod and both the charges have a mass m mass of charges. Light rod given some small angular displacement. So we will give a small angular displacement to this rod from its initial equilibrium position. Question is, find the time period of frequency as it oscillates about some equilibrium position like this. So it is fixed at this particular end. At one end it is hinged, plus Q charge is hinged, and minus Q charge is free to oscillate about the electric field like this. What is the frequency of that oscillation? So let us evaluate. We can simply say that what is the direction of force acting on this negative charge would be in this direction, QE. Its magnitude would be QE. We are given this plus Q charge is a hinge charge. So even if a force is acting on it, QE in this direction, it is balanced by some hinge force H acting on the Q charge. Now this whole system is going to oscillate in such a way that the angle at which it makes with the electric field is theta. This angle is given as theta. So you can say if this angle is theta, then this angle also becomes theta. So what is the torque due to this electrostatic force? So torque due to QE force is QE. Now it will have a component along this direction, that is Q sine theta. This is QE sine theta into the distance at which this force is acting, the line of action of force. The line of action of force is at a distance from this plus Q charge. So this is the torque. Torque is equal to AQE sine theta. This torque is producing the angular acceleration alpha in this system whose moment of inertia is ma square and angular acceleration is alpha. So this is the equation tau is equal to I alpha. Here moment of inertia for only a single charge is taken as the other charge is hinged. It is its distance from the point of oscillation is 0. So that's why only one uh, particle has a moment of inertia. The other particle has 0 distance. So it's ma into 0 square plus ma square. Upon solving this, so uh, we'll say E Q E. This sine theta is very small, so this will become theta. This will become ma square. A and A cancel, and this is alpha, which is d2 theta upon dt2. So what is the coefficient of theta? That is QE by ma. That will become equal to omega square. From this we can write QE by ma square root is equal to omega, or time period of oscillation is equal to 2 pi square root ma divided by QE. So this is the answer which you are looking for. Time period of oscillation 2 pi square root ma upon QE, because omega is equal to 2 pi by t, and whatever the coefficient of theta is, that is omega square. So QE by ma, that becomes omega square. Thank you for joining.